Great. Can you guys see the slides now?
Yes.
Awesome. Cool. All right. Hey, everyone. Welcome. Thanks for coming to a talk on a Friday afternoon. I know it's not the easiest time. Ida reached out to see if I'd be happy to give a talk at ACM. So that's what we're here for today. And I'm going to talk to you about AI for tropical cyclone forecasting, which sounds like a bit of a random topic. But hopefully I can give you a bit of context on sort of the general field of weather forecasting and how we eventually arrived at the specific topic of forecasting cyclones. My name's Andrew. I'm a research engineer at DeepMind, and I'm part of the weather effort. So this sort of work lives part of much of the work that DeepMind does around forecasting the weather. Slides. Great. Okay, cool. So yeah, I thought I'd start by giving a bit of a personal background. I also just realized I think the photo on the right is very stretched out. My face looks really wide. So I did my studies at Imperial College here in London in maths and computer science. And then I was an intern at DeepMind in the summer of 2023. And then I joined full-time as a research engineer in January 2024. So just over 2 years that I've been working full-time on the weather effort. Okay, so taking a step back, how did we get here? And specifically what I mean by this is, how did we get to forecasting cyclones? Because as I said, that feels like quite a niche topic, and one that actually I know quite a few people always ask, why is DeepMind forecasting cyclones? Well, it all really starts in this focus on medium range global weather forecasting. So specifically, what do I mean here? I mean the task of trying to predict the state of the atmosphere, that's the atmosphere everywhere on Earth, up to 15 days into the future, in all 3 dimensions. So not only on the surface, but as this diagram on the right is showing, also in the vertical elevations above the surface, and for multiple variables. So these variables look like the following, like what's on the bottom of my screen. Here we've got surface winds, the middle is surface temperatures, and the bottom right is specific humidity. So really the task is getting these variables predicted 15 days out into the future. And it's not just DeepMind that's taking an interest in this topic. There's quite a number of approaches that have popped up over the past few years. This includes things like using CNNs, GNNs, which you'll hear a bit more about in a moment, some Fourier neural operators, if those of you have come across NVIDIA's work, and then most recently transformers, which I'm sure many of you have heard of, especially if you're interested in machine learning. And usually at this point, people say, okay, that makes sense. But what does the data that you're training on actually look like? What is it that you guys are actually forecasting in terms of weather data? And typically these models, all the ones that I've just listed and the models that I'm about to talk about, which we've trained, are trained on a product called reanalysis. And typically you'll hear of ERA5, which stands for Earth Reanalysis, made by ECMWF. This is the European Center for Medium Weather Forecasting. And really what this reanalysis is, it's the product of taking a whole bunch of observations around the world, from satellites, radiosondes, rain gauges, surface stations, and then solving what we call an inverse problem to assimilate it into a dense gridded state. So the problem basically asks, okay, I've made all of these sparse observations. What would the state of the atmosphere have to have been to have given me these sparse observations? And importantly and very conveniently, the output of this is exactly what I've said as a dense gridded state. And this homogeneity is very convenient for us. For those of you that have been playing around with machine models recently, this literally looks like a tensor where one of the dimensions is like the latitude, the other is the longitude, the others are vertical elevation, and then the other is just the variables that we're actually trying to predict. So this makes the task of training a weather model on this data much easier to do this way around than trying to train it straight on the sparse data. Okay, so specifically at DeepMind, there's 3 main seminal pieces of work that we've published to get to the point of eventually what I'll talk about in cyclone forecasting. The first was GraphCast, which we published in Science back in 2022. This was right before I joined the team. The second was GenCast, and this was the first piece of work that I was part of, which we published in Nature in 2024. And then finally, FGN. This is our most recent model and the model which the cyclone forecasting is based off of. So let's break it down, starting with GraphCast. And for the first few models, I'm just going to give a very quick overview to give you a flavor of how we've reached to this point, but I won't go into too much detail. GraphCast, sorry, I'm not sure what this yellow blob is here. GraphCast really boils down to being what we call a learned simulator. It's simulating how the atmosphere evolves on Earth. And it's based on GNNs, graph neural networks. For those of you that aren't familiar with graph neural networks, they're really just a type of machine learning network that focuses on learning interactions between entities. So usually the GNN has some nodes and edges, and the idea is to learn over time via a process we call message passing, how these nodes influence each other via these edges. And in our case, you can really think that this translates across to nodes being like points on the surface of the Earth. And we want to learn, how does the weather in certain points on Earth affect the weather on other points on the Earth? So in the case of GraphCast, we take the input weather state, and this is the state everywhere on Earth at the current point in time. And actually, we've skipped out a detail on this diagram, but for GraphCast, we take the current state of the weather and the weather 6 hours ago. And then via the network, the task it's asked to do is to predict the next state, so the state of the weather in 6 hours' time. And it does so in 3 stages, 3 main components. The first component is what we call an encoder. It goes from this gridded state of the weather all around the Earth onto what we call a multi-mesh. And this multi-mesh is our way of representing the Earth as a graph. You know, we've simply said, okay, now the graph, like the Earth is actually a sphere. It's not this gridded data. And we'd like to represent it as such. So we're going to create this close to spherical mesh made of multiple nodes. And that's where we're going to do our learning. We're going to run our GNN on top of this processor, or the processor is going to run a GNN on top of this spherical mesh. And then finally, we need to get back to the weather state. And that we do via something called a decoder, which is another GNN. And this is exactly what gets us back out to the next state. So you can think of sort of this 3-step process that gets us to the next state of the weather. And then to get a forecast all the way out into the future, we simply do what is called an autoregressive rollout. So we take the output of GraphCast 6 hours into the future, and then we feed it back into the network. And from this, you get an autoregressive rollout, take it, feed it back in, take it, feed it back in. And that's how you get all the way repeatedly into the future. In terms of training GraphCast, it's quite an ugly expression that I've just put on the bottom of the slide. And really the point that I'm trying to make is not at every single term and every single expansion of this expression. So really, I'll blur all of that out. The main thing I want to focus on is that GraphCast is trained with just a mean squared error. So really what this boils down to is we've said to GraphCast, you spit out your prediction, and I'll tell you how close you got to the actual ground truth. And then the standard process of machine learning of computing your objective function and then back propagating through it, that's how we train the network. And importantly, I'd like to call out that this is a deterministic objective function. We've said to GraphCast, you give me your best guess and nothing else. And I'll come back to in a moment why that's important, or actually, a bit of a discouraging thing to do. Okay, and then if you go and read the GraphCast paper, it's 150 pages long, so some great weekend reading. But I'll really take like the main sort of headline result from it. And that main headline result at the time was that GraphCast outperformed the best operational system, HRES, which was made by the European Center for Medium Weather Forecasting. And in particular, HRES is just your traditional numerical weather forecasting model. It's a numerical solver that takes a bunch of fluids equations, like Euler's equations that approximate the atmosphere, and it rolls it out forwards in time. And it's what ACM WF use as their best deterministic forecast, and we beat it. So what you're looking at here are just plots of the root mean squared error of a specific variable, in this case, geopotential, as a function of time. So 2 days, 4 days, 6, 8, and 10 into the future. The black line is the error that HRES admits, and the blue line is the error that we GraphCast admit. Importantly, lower being better, and the blue line is below the black. Otherwise, I probably wouldn't be presenting to you about this model today. Another way of representing the same exact plot is with these relative RMSE differences. So what you're looking at here is just literally like as a relative proportion, the gap between the two models. And so like this gap over here corresponds to this gap down here of about a 10% improvement. And bear this idea of relative errors in mind. It's going to pop up a bit later on in the talk as well. Some other variables: surface temperature, surface wind, specific humidity. The long story short is for all of these variables, we outperformed. Specifically in the GraphCast paper, I think 91% of the variables we beat HRES on. And 91% being all of these variables at all of these elevations across the Earth, all the way into the future. Okay, so then came GenCast. And what was the motivation behind GenCast? So I hinted in one of the previous slides that the biggest letdown with GraphCast is that it's trained with a deterministic squared error. And importantly, what this means is that you really have no sense of uncertainties, probabilities, or statistics, and you're extremely unlikely to predict extreme events. And the reason for that is, like, if you think about what a task like this is going to encourage the model to do, is it's going to encourage GraphCast to just hedge its bets. You know, I'm saying to it, you've got one shot at giving me your prediction, and I'm going to impose your error on this. And if that one shot is bad, then you get a bad penalty for it. And so GraphCast's not going to try and make these very outlandish claims about what the weather might be. Instead, for these types of models, we say that they undergo a phenomenon called blurring, which literally means the forecast looks blurry. And I'll show you this in a couple of slides. So instead, we do want this uncertainty. And that's where we'd like to switch to a probabilistic setup. And specifically in this probabilistic setup, what we say, the ensembles enter the picture. So what do I mean by this? What I mean is that instead of asking the model to only give me one prediction of the future, I'm going to give it the opportunity to give me multiple guesses of what the future is going to look like. In particular, from a starting weather state, we can roll out multiple possible trajectories of where the weather is going to go into the future. And from this, I can construct my distribution, an empirical distribution of what exactly the model, what exactly the weather may look like in the future as a distribution. Cool. So in GenCast's case, and again, I won't go into this in too much detail, but feel free to ask me some more questions at the end of the talk. In GenCast's case, we use a diffusion model. And really the task here is to mirror or to model some distribution of X conditioned on some Y. And again, not to make this too mathsy, let's look at some actual concrete examples of what this is. Many of you have probably played around with these new image models. I guess more recently, they perhaps have moved away from being strict diffusion models. But if any of you have played around with things like DALL-E or Imagen or Nano Banana recently, although as I said, that's sort of moving away from that. In those setups, it's like a text to image diffusion model. Your X is the image that you're trying to output, and the Y is the text, the prompt that you of the user has put in. So we're making an image condition on that prompt. So for example, I say, my text Y is, I want a photo of a cute dog. Conditioned on that phrase, cute dog, we generate an image from some noise that looks like this. And really, this is the diffusion process. Let's take some noise, and from it, let's denoise to get the actual final output X. And so let's translate this across to weather. Well, in weather, we're not going to do text to image diffusion. We're going to do many images to many images diffusion, where Y is going to be many images of the current and past weather. And then X is going to be the future weather state. So I'm saying, conditioned on the current and then the previous weather, what's the weather going to be like in the next state? And again, we start from some random noise. And the idea is to denoise conditioned on these current and past weathers to actually get our future weather state. And so I mentioned this idea of blurring. And I like this slide here because I think it really demonstrates the difference in what it looks like to get a probabilistic ensemble forecast and a deterministic forecast from a model like GraphCast. So what you're looking at here is I've just picked a region of the Earth that may or may not contain both where you guys are and where I am right now. And we're going to look at a random point in time. This was the 20th of September, 2018 at 6 p.m. And this is a variable called specific humidity, which is a nice variable to use as an example because it's quite a sharp one. And I basically said to GraphCast and GenCast, hey, I want you to create a forecast of this point in time, but all I'm going to give you is information from 12 hours earlier. So, in this case, I'm going to initialize it on 6 p.m. on the 19th of September. In this case, I'm going to initialize it on information from the 5th of September at 6 p.m. And in this case, on the 15th of September at 6 p.m. And in this case, on the 10th of September at 6 p.m. So I'm sort of starting it off from further into the back. In GraphCast's case, okay, the forecast from 12 hours earlier looks pretty good. I mean, again, this matches quite closely with the ground truth. Again, I probably wouldn't be giving you this presentation if that wasn't the case, but it's sharp. It's nice. I see these features in the forecast and they match quite closely. But then if I look at 5 days earlier and 10 days earlier, look at this bottom frame and how blurry this section of the forecast becomes. It's really, GraphCast is blurring. It's trying to play it safe. It doesn't want to make a bit of an outlandish claim and get penalized on the error. In GenCast's case, okay, let's go 12 hours earlier. You might have to squint a bit to realize that this is an animation. So there's slight variations in the frame. And in particular, it's because I'm actually displaying different samples that have come from GenCast. But all of the samples look quite close to each other because at this point, it's quite close to the actual event. It's only 12 hours before. So GenCast is pretty confident. It's quite sure it knows what's going to happen. And then if I look at 5 days and 10 days earlier, okay, the samples all look quite different now. That's GenCast's way of expressing its uncertainty. But every sample is still sharp. Look at how each of these still have these very important local features and don't blur. And that's the difference, is that GenCast can express its uncertainty by just creating a different distribution of samples, whereas GraphCast has to express its uncertainty by blurring the deterministic forecast that it generates. And if I wanted to have like a single forecast because I didn't want to deal with ensembles, I can just take the mean average again across the samples, and I recover the sample mean. And again, you can see that that's blurry, just like GraphCast. Cool. Again, you can go read the GenCast paper. It's another 100+ pages, so maybe that's for next weekend reading. The important part in GenCast is that GenCast outperforms its baseline. And for GenCast baseline, again, it's the top operational system from ACM WF. In this case, the ENS ensemble forecasting system. And here what you're looking at is what we call a scorecard. So a scorecard is just a gridded way of me displaying what I was showing you earlier with those relative plots. In particular, if you look at the scorecard, again, the x-axis is just lead time. It's how far into the future the forecast was. Each of these big boxes is a specific variable like temperature, geopotential, and so on. Or here, it's a surface variables, 2-meter temperature, some surface winds. And then these like columns here are if the variable is defined on normal notations. And in every single square that you're looking at here, the color indicates which model was better. So blue says that GenCast is better, and then red says that ENS was better. So if I pick a specific square here, I'm saying, okay, at 3 days into the future, for the 500 elevation of the V component of wind, GenCast was 10% better than ENS. And luckily, you're seeing a lot of blue here. Again, otherwise, we wouldn't be here. The specific difference, though, is the metric you're looking at here is no longer the mean squared error. And the reason for that is that the whole point of what we're trying to do here is we're trying to get a good probabilistic forecast. So it wouldn't really make sense to then go back and check how good the model was at the deterministic task of predicting a forecast with a low error. Instead, we use a metric called CRPS. And the CRPS, it stands for the continuous ranked probability score, yada, yada, yada. The important detail is that really what it looks at is it tries to compare the distributions. The distribution of your prediction, which is sort of in this like simplified diagram as the blue line, and the distribution of the actual event that occurred in the weather forecast. And importantly, only one event actually occurs in the weather, right? Like you either rain or you don't. There's either some temperature or there is. And so that distribution is just a step function, or in particular the CDF, it just doesn't happen. And then the thing happens and then you're just one from there, that point onwards. So really what we're looking at is we're just getting in this metric a computation of these values, the differences between the two distributions, and we want them to be as close to 0 as possible. Okay, so I've spoken about our sort of 2 stepping stones along the way to creating FGN, which is the third paper. And importantly, FGN is the model that we eventually use to do the cyclone forecasting, which is the culmination of what I'm going to talk about in this talk. In FGN's case, first I'll start again with a bit of motivation. The problem is that diffusion is expensive. And I mentioned this like denoising process where we've gone from noise, and after a bunch of iterative steps, I end up getting a cute dog, or in GenCast's case, a weather forecast. The problem is that GenCast needs 40 denoising steps. And if any of you do work with diffusion, you might know, like, yeah, we can probably bring this number down using a couple of techniques, but still, there's a greater than 1 number of forward passes that I need to take in my model to get my actual probabilistic forecast. FGN is 8 times faster. So really, one of the motivations of FGN was let's find something that's faster. We can generate an entire forecast of FGN for 15 days into the future with 50 ensemble members in about a minute, which for reference, the traditional models that I was referencing, like HRES and ENS, take about a couple of hours. So already GenCast was fast. It was like an 8-minute model, but FGN is even faster. And the second is this idea in machine learning of, you get what you train for. So what I mean by that is, okay, we really want to evaluate these models on CRPS. But actually, in the case of GenCast, the diffusion setup doesn't train a model on the CRPS target. It actually specifically trains a denoising target, which I won't go into too many details, but ends up with a denoising training target of a mean squared error. So I'm happy to answer questions about that in the end. And so it kind of comes back to this idea of, okay, we're eventually going to evaluate the model on this CRPS metric. Why don't we just directly train on CRPS, which FGN is? And the outcome is that FGN is better than GenCast. It more than doubles the gap with respect to ENS. So GenCast was already better than ENS, and FGN is even better than that. And to give you a bit of a flavor of some more intuition about the CRPS metric, because I think it helps to understand, you get what you train for, but how do you know this is what you want to train for? So I showed you this diagram on the previous slide, but I would actually like to break down this metric slightly mathematically. Importantly, one way of writing CRPS is in the following expression. It's what we say is the expectation, so the error minus the variance. Or importantly, in an intuitive sense, it's how much did your forecast actually deviate from what the ground truth actually was, subtracted by how much did you demonstrate in your forecast that there was different possibilities. And the reason this is important is what this basically tells the model is, okay, either you get the error down to 0, so your forecasts are so good that every ensemble member looks exactly like the ground truth, in which case there's no variance, and so this guy goes to 0 and that guy goes to 0. Or we say to it, if you want to make errors, that's fine, but if you made errors, you better have shown us that you were unconfident about these errors. So don't go give us a very overconfident prediction about the future weather and then still get it wrong. And so mathematically, again, it's like if this number is big, that's fine, because you can cancel it out by making this number big. And then you can still get a low error on this. So more deviation from the observed outcomes should come with more uncertainty. Awesome. Okay, so I've given you all the motivation. I've told you how great FGN is. How does it actually work? So I'll start by showing you how FGN actually runs. And then we'll work backwards to show you how we actually train FGN. In FGN's case, we take a single input sample. So we just take, again, as the last two models, it's the current state of the weather. Here we've noted it as T-1, and then the weather right before that, T-2. And then we take something called a noise vector, or specifically the process we use is something called noise injection, which I'll give a bit more detail about in a second. And with this noise injection, we get the FGN network to spit out a prediction of the future weather. That's one ensemble member. Then we do this a repeated number of times, each time sampling a different noise vector, but with the same input sample state. And from that, I generate my ensemble of predictions. And this is the stochasticity in FGN. So in GenCast's case, it was like a different starting noise to denoise from. In FGN's case, it's a different noise injection into the network to generate an ensemble of predictions from. But two important things about this noise injection. The first noise injection, or the first important detail, is if any of you have worked with like probabilistic models, you might be used to the idea of perturbing the inputs to the model. So, this is what some people do in the literature. It's like, okay, I have my current input sample, and I'm actually going to add some noise to this guy. And from the perturbed inputs, if you think of like a differential equation and you're perturbing your initial conditions, I'll get different outcomes from it. In this case, though, we actually are perturbing the actual parameters of the network. So our FGN network in here has a bunch of layers called layer normalization layers. And these are layers that, as the name suggests, normalize the sort of intermediate outputs of our model. And into this normalization, we're injecting noise. And so this is like a parameter space perturbation. And sometimes it's called adaptive instance normalization. And importantly, we find that this works much better. The main problem with perturbing your inputs is you get exactly overconfident forecasts. The second important thing about this noise injection is we say it's very low dimensional. So if you think about the actual like dimensionality of the weather, it's a very high dimensional problem. You've got your like spatial dimensions, your temporal dimensions, and then you also have the dimensionality of the actual like combined different variables that you're trying to predict, some like order million dimensionality in that sense, just to hand wave a little bit. But the dimensionality of this injection is 32. It's simply a noise vector with 32 dimensions in it. And this is an important thing that we've come to learn, and I'll come back to it in a moment exactly why, but we find that this low dimensional noise injection really helps make the model coherent. It means that it generates these nice complementary forecasts of the whole world, as opposed to focusing on specific pixels one by one. And for those of you that are interested in like uncertainty around networks, also happy to answer some more questions at the end. We say that this models what we call aleatoric uncertainty. And that's the type of uncertainty in machine learning that's just inherent to the problem from the model's perspective, like an inherent uncertainty that you can't really do anything about. Okay, Then let's add one more complication, because unfortunately the picture is not that simple. There's a second type of uncertainty that some of you might have heard of, which is called epistemic uncertainty. And this, if any of you have taken like a philosophy class, you've definitely heard the word epistemic before. It's sort of an uncertainty in the knowledge. And in this case, in the machine learning context, epistemic uncertainty refers to uncertainty that's due to the fact that you just have a finite amount of training data. You don't really entirely, infinitely capture the problem you're trying to solve. And also the algorithms we use are imperfect. As much as we'd like to think that we've figured it out and we've created a perfect algorithm to model the weather, we haven't. And so to counteract this, we use a very sort of traditional technique that is used around a lot in machine learning, which is called model ensembling. And very confusingly, the word ensemble is now popping up twice here. The first one is we have a model ensemble. And then the second place that you're going to hear me use the word ensemble is in the ensemble of predictions. And so what do I mean by this? Importantly, when we actually run FGN, when I refer to FGN, I'm referring to 4 different model instances. We've actually trained the same exact network 4 times, 1, 2, 3, 4. The only difference between it being we've just used different random noises within the training. So that's how they vary from each other. And then for each of these model instances, what I might call a model seed, I do the process that I just described on the previous page. So I take my single input sample, I take that model, I inject noise into it, and then I pop out the ensemble of predictions for that model. So in this case, everything that's labeled yellow corresponding to that model seed that's in yellow. But then I've also got my other model seeds. So in this case, I've got model 2. Similarly, I inject noise into model 2, I spit out model 2's ensembles, and so on. And then from that, I get my sort of meta ensemble of predictions. In practice, we generate 64 ensemble members from FGN, and really breaking it down, 16 of those came from seed 1, 16 came from seed 2, seed 3, seed 4. And each of those 16 came from a different noise injection. So in this case, we say that we're modeling 2 types of uncertainty: the aleatoric uncertainty via the noise injection, and the epistemic uncertainty via the model ensemble. Cool. Okay, so we've worked backwards. I told you why it was such an amazing model. I've told you how we actually run inference to get a weather forecast. Now, how do we actually train it? Actually, the training is not so different from the inference. We're in the same setup. I've got my single input sample during training. I give that to the model, and I inject noise twice. I say, give me your first forecast, give me your second forecast. And then, as I mentioned, we train it on a CRPS loss. And from this, we get our model. It's really, during training, trained with these 2 samples. And then at inference, I can run it with as many noise injections as I want. And importantly, the reason we can do this is that we use what we call a fair estimator of the CRPS. It's unbiased. So the fact that we're using 2 samples in training, but not more, doesn't make a difference. And to revisit this idea that I pointed out about the noise injection, I really want to make like a clarifying point about the CRPS loss. The CRPS loss is what we say a marginal loss. And what I mean by that is like, we only ever penalize the model on a pixel by pixel basis. So in this forecast that is here, there is going to be some pixel somewhere for the grid, the cell that corresponds to Beirut. Then there's going to be a ground truth value of what the actual temperature was in Beirut. And then I'm going to compute the CRPS loss on this pixel at that point in time for that variable. It's a what we say, it's a marginal task. There's no concept of like joint distributions across other spatial areas or times, or even variables. And importantly, it turns out, and we'll see in a moment, that even though FGN is only trained on marginal tasks, it does a really great job of still forecasting joint tasks. And if you go and read the FGN paper, the title is actually Skillful Probabilistic Joints from Marginals. And really, it's to notarize the fact that it's quite a pleasant surprise that you can take something, train it on a marginal task, and still get back good joints. And I'll demonstrate that in a second. So just to wrap up the training of FGN itself, you might wonder, okay, what's the actual model architecture? Super similar to GraphCast: encoder, processor, and decoder, except just like in GenCast, we swapped out the processor for a transformer. And that's why I said at the very beginning of the talk that even us more recently have moved on to using transformers. And the reason for that is just that a transformer is much more memory efficient. We can use things like flash attention and these like very efficient algorithms for computing the relationships between entities. And in particular, in the case of this transformer, the way that we model this relationship between entities is via a node-wise attention. So if any of you have been playing around with transformers and language models recently, you might have heard of the idea of this attention mechanism. In the case of language models, the attention mechanism is like token to token. It's word to word in your sentence. In our case, the attention mechanism is node to node. It's these nodes on the sphere. How did they impact each other? And we do it via what we call an attention neighborhood. So we choose a number, I think it's 32, and we say, okay, for every node, I'm going to attend to any other node that was at most a 32 hop away from that node. And by hops, you can see it's like these edges here. So sort of this is 1, 2, 3, 4, and you can see that you end up getting these regions around the world that are all attending to each other. And then in terms of actually rolling the model out, it's also autoregressive. I start with my single input sample. I've injected all my noise, and I've got out my ensemble. And then now for the rollout thereafter, I actually do start with an ensemble of inputs. So I roll out directly on those to get my following step. So importantly, just to clarify here, I don't get this like tree branching thing. I'm not taking 64 members and then from each of those 64 making another 64. I'm taking one, I get 64, and then I sort of continue them on in a line to roll all the way out to 15 days. Cool. So is it any good? Well, I think I already said to you, yes, it is. Here's the same scorecard that I showed you for the sort of framework scorecard of when I showed you GenCast versus ENS. Here I'm showing you FGN versus GenCast. So GenCast already beat the state of the art, and then we've beat it even more. In fact, we've beat it on 99.9% of targets. So this is how much better FGN is better than GenCast, and the other one was how much better GenCast was than ENS. So as I said, we've more than doubled the improvement on top of ENS. But what about the joint structures? Because this is still a marginal evaluation. I've still gone and I've found every pixel, and then I found the error across every pixel, and then average those errors. So we also in the paper do a lot of evaluations on these spatial structures. And this is one of maybe 10 of those evaluations, just to give you a brief taste of it. In this case, what we say this is a pooled spatial evaluation. We've taken the Earth and we've split it up into these circular patches. And then in these circular patches, we do a transformation of the data. So in the left-hand side, it's an average pooling. So we take that circle and then compute, for example, the average temperature. And then we compare that to the actual true average temperature. And in this case, it's a max pooling. So again, we take the circle, we take the max temperature in that circle, and then we compare it to what the actual max temperature was in that circle. And again, we see that FGN outperforms GenCast, which was a model that was trained with these joints. And this is really what's fascinating about this model, is that it was never trained on having to care about these joint distributions, the average across a space, and yet it still does amazingly well at them. And sort of the running hypothesis for that is that it's because of this low dimensional noise vector that it's able to constrain the model's output so well. Okay, so at this point, I've been talking for 30 minutes, and you might have realized I still haven't said anything about cyclones. So let's actually talk about cyclones now. And this is where our final, or sort of our most recent model, FNV3, comes in. And FNV3 is modeled off of FGN. It's just an extension of FGN. And I'll explain in a moment how it is an extension of that. But just to give you a bit of background of how things worked with cyclone forecasting up until now. So up until now, most cyclone predictions were what we call analysis-based. And importantly, maybe you guys are probably sick of this now. I've shown you this type of diagram about 10 times in this talk. We've got our initial state, we've got FGN, and we're getting a forecast 6 hours into the future. And then we roll this out autoregressively, and that's how we go sort of all the way out to 15 days. In this case, I've cut it off at 4 days. And up until this point, mainly cyclone forecasting was done with what we call these heuristic vortex trackers. So what this looks like is you literally take the analysis output, the analysis being this like dense gridded states I described of things like temperature, wind, pressure, humidity, and you use it in order to get a heuristic of where the cyclone is. Importantly, cyclones usually come with specific characteristics. They correspond to like a very low pressure with a very high geopotential energy and high winds. So you can imagine like if you were a human watching a map of these variables moving over time and you saw like a specific circle where there was low pressure, and around that circle you also had a lot of wind and a lot of geopotential energy, you would say, okay, yeah, that's where the cyclone is. And so just imagine doing that, but with a deterministic algorithm. And so from these, we say that vortex tracker gives us these nodes, and then you come and you stitch these nodes together. But there's 3 big problems with this approach. The first problem is that it turns out that these types of heuristic trackers are quite bad at picking up wind speeds. In particular, the actual coarseness of the forecast, yes, we've generated this global forecast, but its resolution is about 25 by 25 kilometers. It usually dampens out the wind. And it specifically dampens out the wind when you have such a fine process going on like a cyclone. And so the tracker can sort of do the best with what it gets. If you give it winds that seem a bit soft in your forecast, it's not going to go and try to say that there's stronger winds than that. It can at most bias correct it, but it won't do much better. The second thing is that these vortex trackers themselves are quite bad at determining the size of the cyclone. And then what is the actual space around these nodes that are going to be impacted by the presence of the cyclone. And the third is we say they're very bad at a specific phenomenon called rapid intensification. And in rapid intensification, the idea is, okay, can I correctly predict if a cyclone goes from having pretty weak winds to all of a sudden jumping up and being a very strong cyclone? And if you think about it, those are the worst type of cyclones because those are the ones that strike human populations the most unprepared. All of a sudden, humans are expecting this really weak cyclone to hit. And then in the space of 12 or 24 hours, it goes to being like a category 1 to being a category 5 cyclone. And these categories describe the strength of the winds. And those are the worst to deal with. And these vortex trackers are particularly bad at dealing with these rapid intensifications. So what do we do with FGN? Well, we add to it what we call end-to-end cyclone direct predictions. And I think you might think like, yeah, it's pretty obvious, just train it to output the cyclones. It turns out that it just wasn't so easy to do that until a model like FGN came along. Importantly, we've taken a data set called the IB Tracks data set. This stands for the International Best Tracks. It's like the best recorded knowledge of track locations. And they're literally a data set that contains latitudes, longitudes, wind speeds, and pressures of these cyclones. And this is actually just a visualization. It's an animation of plotting these IB track data points as a function of time, sort of for the past 20 or 30 years. And you can see, you get a lot of activity in the Atlantic and the Pacific, and it also comes with these corresponding categories. So that whole process I just described to you of how we train FGN with the samples and the CRPS loss, we add to it, asking it to produce 2 samples of where the cyclone is actually going to be and what its wind speeds are and what its pressure is going to be. And then we compute the loss and we play the same game. And so these sort of arrows are supposed to demonstrate this addition of the tracks to the training. And then in terms of actually getting our end-to-end cyclone predictions at inference, now not only do we have these predictions that are making the analysis fields that we sort of are standard weather prediction fields, but we're actually also outputting directly the properties of the cyclone. So we're saying every latitude and longitude where the cyclone is, the maximum speed of the wind, and also these extent fields. So really they demonstrate like where is the circle around the cyclone that I have winds of a specific 34 knot speed? Where do I have the 50 knot speed and where do I have the 64 knot speed, the extent of the cyclone? And from this, we track. So again, I directly output the forecast of the node, and then I stitch them together. And now we have a much easier task. We just have to stitch the nodes that the model's already saying are there instead of having to heuristically guess where the node is. And we also directly get the category of the winds and the extent of them, which I'm sort of demonstrating in this diagram here. And what's great about this is, as I said, these are a probabilistic model. And so I don't just get one guess of where this is going to be. Maybe I could have considered doing the same idea with GraphCast, and actually that's where we started. But instead, I'm doing it with FGN, so I can get 2 predictions of the paths the cyclone is going to take, 3, 50, or even because FGN is so cheap to run, we actually in real time run 1,000 ensemble members. So we're always constantly providing 1,000 possible forecasts of where the cyclone is going to go. Obviously, with the majority of those forecasts agreeing with each other, but still, this really allows us to capture the extremes and the uncertainties of what might happen to the cyclone. And what's nice about these 1,000 ensemble members is they really, as I said, capture the fine details of what might occur. And so we can generate these super useful mask plots that we've actually been providing and working with weather agencies on. So importantly, here's like a probability mask plot that's asking the question. This was actually a specific hurricane, I think Beryl, back in 2023. We asked ourselves the question, at this point in time, what is the probability that the wind that the cyclone is causing is going to cross a specific threshold, aka more than 34 knots, more than 50 knots, more than 64 knots. And importantly, the reason we want to ask ourselves that question is it's like, okay, in the next 4 days, where should I expect and with what probability that places are going to be impacted, and do we need to make decisions off of that? Should we be evacuating people from those areas? And so you can see that like the sort of weakest storms sounds like quite a few places are going to be affected by that. Severe winds, less. And then the category 1 cyclone winds, it's a very, very narrow band. But it probably sounds like, and I think in the end it did occur, that this is going to be quite an impacted area on the coast of Florida. Okay, so last couple of slides, really to round this all off. I could have showed you those slides and just been like, yeah, it's a proof of concept, but it doesn't work so well. Fortunately, it works very well. And we've actually demonstrated that FNV3 is the state-of-the-art cyclone forecasting model, at least based compared to a number of globally used baselines. Here is its comparison on track error. So you're looking at, again, like how far into the future am I predicting, and how far off were the tracks from where the actual cyclone track occurred. And so obviously the error is going to go up with time, but luckily for FNV3, it stays the lowest. Again, for intensity error, so how good of a job did we do at predicting how strong the winds were going to be? It goes up with time, but FNV3 stays the lowest. And finally, for the extent error, it goes up with time, the extent being where the cyclone is going to impact, but again, it stays the lowest. And so, we really think we believe we've created a state-of-the-art cyclone model here. And then for the final slide, I'll just point out that actually we share these forecasts in real time. You can go and visit it right now at deepmind.google.com/science/weather lab, where you can literally see the forecast of a number of our models. In this case, FNV3 is the experimental model that's labeled here, compared to GenCast, GraphCast, which are running with these heuristic trackers that I mentioned, and then the baselines from ACM WF. So I'll quickly show you guys what that looks like. This is a live demo. There you go. So now there's not much activity happening now in the Pacific or the Atlantic. It mainly is happening around Australia. It's their sort of hurricane season right now. So you can see these are live forecasts initialized from this morning. And I can play it forwards in time to see where FNV3 is predicting that the cyclone is actually going to go. Awesome. So yeah, finish off by saying thanks and also pointing out that this is really work done by a large team. I'm one of many contributors to this work. In particular, the faces I've got up here are people who are directly involved with the cyclone side of this, but there's also a lot of other names to thank for previous work like GraphCast and GenCast. So thanks. And yeah, let me know if there's any questions.
First of all, Andrew, thank you. This was genuinely a wonderful, beautiful lecture in a session,
Awesome.
more preferably to say. And honestly, there's not much to say after what you said. So if anyone has any questions, feel free to type them in the chat and I'll read them to you, or you can read them directly within the chat. One
Awesome.
rather straightforward or simple question is, why do you still call it experimental model instead of calling it FNV3?
Yeah. That's a good question. I think the reality is like when we put this website out, we have to be a little bit careful in that we're at DeepMind not trying to become a weather agency. Really our like fundamental goal is to support weather agencies to make their own decisions. There's also like a lot of legal frameworks in place for this. So there's a lot of countries where it's illegal for us to disseminate forecasts to the public that don't come via the weather agencies. And so we're really trying to highlight to people that these are experimental forecasts, that we don't want people to be making direct decisions based off of them. But simultaneously, while Weather Lab was running, at least in the most recent American hurricane season, we partnered up with the National Hurricane Center, and they were using exactly sort of what you're seeing on Weather Lab, those exact forecasts, in order to make judgments on the alerts and the forecasts they were sharing out to members of the American public. And so that's sort of our preferred route of doing this. It's let's go through an agency and let the experts make the decisions based off of our forecasts.
Mm-hmm. Makes sense. And what would you say or you describe as the most difficult parts maybe even about these projects? Is it the ideation, problem formulation? I think the problem is whether sometimes self-explanatory since you started from somewhere and then you moved forward, but then is the
Yeah.
ideation, is the experimentation, testing, evaluation. What exactly would you say that's the difficult part in this pipeline? The most difficult?
Yeah. I think like one of the most difficult parts is a lot of people underestimate the difference between training like an experimental weather model in a very like easy environment. You just like, you've got your data set, you train it, and then you get great results. That versus actually running a model like this in real time, and using it in order to get real-time forecasts. And I think that's a research question, like what does it actually mean to run on data you're receiving in real time that hasn't been cleaned, like data that you get in existing data sets that are historical? But also, like, what does that mean operationally? Now you need to care about how fast the latency is. And like, yes, FGN is a fast model, but you need to care about how quickly you're able to ingest the data, how quickly you're able to send out the forecast, how quickly you're able to do all the processing around it. So I think for me, at least as a research engineer, it like sits exactly in the middle of the types of questions that I'm super interested in exploring, of like, how do you actually do research and also combine it with engineering? Because it's one thing building a model that sits on your shelf, and it's another thing actually running it in real time.
That's very logical. Cool. So, does anyone have any questions? Feel free to ask. You can go technical. You can go.
Yeah,
Take
please
take
do.
advantage of Andrew's presence.
How vulnerable is Lebanon to cyclones? Yeah, not really. As far as I'm aware, like the Mediterranean doesn't really suffer from cyclones per se. I mean, but I guess it also depends. Like, a cyclone is a specific. It's like a designation. Oh, thanks, Cloud. I'll come to your question in a second. So, like a cyclone is a specific designation of a storm. It's like a storm that meets a specific set of criteria. Your pressure has to be this much. Your et cetera has to be this much. And like, obviously, Lebanon is falls victim to weaker storms per se. So, this general ability to be able to forecast these phenomena is incredibly useful. I think cyclones is like an easier way to start sort of, because it's such a big problem that there exists these data sets where people have been tracking cyclones since the 1970s, and so we can train our models off of them. But the better that we become at forecasting the weather, and then specifically extreme weather, the more that I think the whole world benefits from it, and not just areas of the world that are affected by cyclones. Thank you. It was great lecture. You said something about introducing uncertainties for the GenCast, and then when GenCast produces multiple samples, you take the average of the samples. So my question is taking the average considered as this somehow what will happen? When I sent in the last point, that question, does the introduction of uncertainties propagate the number of days increase? Yeah, great questions about it. So let's start. I think your first question was about GenCast. Yeah, I think the main point I was making with the ensemble mean in GenCast is, okay, so I showed you guys this slide where we're generating different samples of the future weather using GenCast. And in GenCast case, the way that we make these future weather states is each of these, what's about to appear now, these like random noises, we sample different noise each time. And this different sample of noise corresponds to a different forecast that comes out of the model. And so, and that's what I'm showing sort of in this middle column over here. These each are the realizations of when we went from noise to an actual forecast. In the case of the ensemble mean, yeah, you can think of that as like the max, I guess the modal likelihood of what is going to occur. We're literally saying like ignore all of the variance in taking into account the variance in the distribution, but flattening that dimension. Just give me the mean average of all of these samples. What is the on average occurrence that's going to happen out of this forecast? Yeah, exactly. So it's on average, sort of the average expected thing that will happen. Is the variance between samples? No. So I'm tying that into the final part of your question. The uncertainties increase as time goes on, and that's exactly what this slide is showing. It's telling us like when I forecasted from 10 days earlier, my samples had a lot of variance in them. And so that's exactly why when I take the average of these samples, I get a very blurry mean average. And then here it's saying when I only made the forecast from 12 hours earlier, there was little variance because the model was quite confident. And that's why its average is still quite sharp. And then you said, to what extent can the last model forecast 15 days into the future as well? And to be clear, in all of these cases, like we decide to cut off at 15 days because that's when like we start to find the usefulness or the error grows past the point of usefulness. But nothing actually stops me from like rolling more days out. I can still auto-regressively take the output and feed it in as an input. It's just not so clear that the accuracy of those final extra days will be of any use. But the model stays stable. Like I think we've rolled these models out to maybe a year, and what you get in a year's time looks reasonable, but it is a very low accuracy forecast. When again, more risk forecast, we prefer to get back to the first model, which is already no. Even then, even in the case where you take, like, even if you just wanted a single like best average estimate of what will happen, you're better off taking the ensemble mean of the probabilistic model than taking the deterministic output of a deterministic model. Awesome. Thanks. Good questions. So Samir asked, thanks for the presentation. I really enjoyed it. I wanted to ask, how do projects like this usually get built? How much time goes into research, choosing and training the model, and when do you start thinking about the overall pipeline deployment? Yeah, that's a really good question. And I think that's particularly a good question because, like, I think it gives a bit of insight to how research like this works in the industry. So maybe I would break it down a little bit to how each of these three guys happened, and then how eventually we ended up with the cyclone forecasting. So GraphCast actually came out of a hackathon at DeepMind. Every year, DeepMind does like a 1 or 2 week hackathon where pretty much the whole company just stops working. And I mean, we don't not work, but we work on a random hackathon idea. It used to be called an extravaganza. And GraphCast came out of a extravaganza. A group of the two main authors on the GraphCast paper, their names are also here. This guy, Remy Lam, and Matthew Wilson. These two started this extravaganza project to see, they were like, oh, can we use machine learning to forecast the weather? And then out of that came GraphCast. And I think that's a reflection of what industry ML research used to look like back in like 2022, 2021. It was a lot more exploratory. It was like, what can we do? Then after GraphCast came GenCast. And in GenCast case, I think it was like, we realized that there was something here. GraphCast had just beat the best operational model, HRES. And the question became like, okay, now that we know machine learning can be used for weather forecasting, how do we actually want to do this? Like, what's the proper way to solve this problem? And we noticed that, all of these image diffusion and video diffusion models were coming out. And we were like, hang on a second. Like, really the weather, when you think about it, is just a video. Like, it's a video where I think this slide demonstrates it. Like, it's no coincidence that this animation is literally a video. It is a bunch of frames that move forwards in time. And so we were like, okay, like surely we can just borrow some of these ideas from image and video diffusion and get from that these nice coherent videos that are actually weather forecasts. And that's how we got to GenCast, and that's how we built it. And in that case, in terms of like the choosing and the building of the project, it was like, no, we actually, the company dedicated resources to it. There's like the team of 10 that worked on GenCast that were focusing on GenCast. And then again, from that point, I think we got GenCast and we were like, okay, we can probabilistically forecast the weather, but it's expensive. How do we turn this into an actual operational model? And that's where the operational side of things comes in. Like, it's like, okay, these models are useful enough that we want to be deploying them, but we need to get the cost down. And luckily, like one of the benefits of working at a company like DeepMind is that you can actually afford, like while we were working on GenCast, the main author of FGN, Ferran, was working on FGNs as sort of his like side individual research project. And he found that it was what he was able to produce a model that was even better and cheaper. And at that point, sort of one of the questions was, okay, we're deploying this. What are some of the other things that we can target in weather forecasting past just the probabilistic? And we heard from a lot of feedback from weather agencies that cyclone forecasting was a really good problem that would be good to try and solve. And I think it was also quite like practical and strategic. It's like cyclone forecasting is a very global problem. You really need to be able to capture the global atmosphere well, and that's what our models do. So we're like, okay, our models should be pretty good at this. Like, we could already see it with the vortex trackers that they were quite good. So we were like, let's do a better job of this. And I'd say that's sort of my insight of how we got to this point. So hopefully that answers your question. Pilot. When training the model, inform it in a sense that, yeah, we expect a rainy week next week. Does the model alter its results? So we don't like, I guess sort of coming back to it, like at the end of the day, all these models are trained with is this type of setup. It's the current weather and what the weather actually eventually was. So in some sense, like we're informing the model it was a rainy week next week only through the fact that we eventually said to the model, you predicted this amount of rain for next week, but it was actually this amount of rain. And from that, it's the classic like machine learning backpropagation of we update the weights of the machine learning model based off of that. And one way or another, in some interpretation, it's because the model is learning how to alter its outputs so that it did actually predict a rainy week when there was a rainy week. But we're never really like as input in addition to giving it the current weather on top of that saying like, this is what we think the weather is going to be in the week. What do you think it's going to be? We're just saying, this is it now. You tell me what it's going to be in the future, and then I'll tell you if you were right or wrong. Awesome. Great questions, guys. Any others?
So I don't know if you can say this piece of information, but for example, looking at the experimental model that you currently have, how do you
Mhm.
look at this and say, oh yeah, we can see that X, Y, and Z take could use some improvement? Like, for example, when you look at this, what do you think is still missing for it to become something that's like even better than what it currently is? Maybe incorporating some extra use cases.
So, sorry, to be clear, is your question like, how do I actually look at these forecasts that are here and say we've got room for improvement?
Yeah, so that's one part of it. And the other part is, for example, let's say that you think that up to a certain extent the improvement would be minimal, then the question could become, how could you take advantage of what you
Mm.
already have to maybe enlarge in the landscape of what you can use it for?
Yeah, so that's a good question. So yeah, I guess like, you know, if you ever like read a weather paper or you read, I guess you read any paper or any research task that involves forecasting what we call a time series, so like a process that varies as a function of time, you will see the same exact trend in all of those papers, which is, and if you don't, this is a red flag. Like if you read a paper that doesn't do this, then my advice to you is that there's something wrong in the paper. If the error doesn't go up as a function of time, then something is a bit suspicious. Um, and so ultimately, like, yes, we look at this and to the very first order approximation, like the simple answer is unless this line goes to zero, we've got work to do. But the reality is that there's also some like intrinsic predictability in these processes. Like we know for a fact from chaos theory, or you might have heard of like the butterfly effect or something, that it's effectively becomes impossible to some extent to accurately predict the evolution of a system because you have this irresolvable uncertainty in the initial conditions of the system. Like I'll never be able to tell exactly what the weather was at the start of the prediction. So therefore I will never be able to exactly predict the weather further into the future. So yeah, we look at this, I think what we're seeing internally yet is that we can still bring this line down. Whether that's with like weather unrelated stuff, so just building like better transformers, bigger transformers, or weather related stuff, getting more data involved and so on. Um, Up until now, like the line hasn't stopped coming down. There's some like theoretical estimates of where the line should end, but I think like time and time again, we're sort of being proven wrong by machine learning per se. So in that sense, we keep going. Now, the second part of your question, like if we do, suppose you came and you were like an oracle that told me you've hit the line, there's nothing else you can do to get the line down. The other nice thing about machine learning that unlocks a lot of capabilities is that it can very easily extend to multivariable tasks. So what I mean by that is like really like this recipe of taking FGN and training it with cyclone variables was so not easy, but was a direct extension of the classic task because it is quite simple to just add more variables to a machine learning model and just impose a loss function on them. And what's also nice about it is that like you have control over the loss function. So somewhere in our loss function, we put like 10% of the weight on wind variables, 10% on temperature, 15% on the cyclone variables, et cetera, et cetera. So if you care about a specific task more than another task, you can also weight those up and down. So even if we hit that line, I think the reality is like machine learning opens the doors to modeling so many more things that we can, get other minimal error lines on other features that we don't yet model with traditional models per se. I hope that answers your question.
Perfect. Makes so much sense. Thank you.
Awesome. Khaled, do you think training on history instead of just the current is a good practice? I guess, can you elaborate on that? Because like in our training per se, like the model that you see that's running on this website has been trained up to data that's just the start of 2025. It's literally like we've trained it on all data going back to 1970 up to 2025. And then we run inference. And we obviously, you can't train on future data because that data doesn't exist. So I guess, can you elaborate a bit on your question? If I remember correctly, you said you give them more the current state, so I assumed you only meant the present. Right, sure, but I guess okay. I think the problem is like, you need to remember the difference between training and then actually running inference. So in an ideal world, along with giving it the current state of the like oh, you said you give them all the current state, so I assume you only meant present. Yeah, so we give the model like the current state of the weather, and we also give it 6 hours in the past. If your question is why we don't give it more of the past, so why don't I also like why do I give it 0 and -6, but not also -12, 18, 24, etc.? It's because we found that like tapers off. Oh, that's your question. Cool. Okay. It tapers off in effectiveness. So specifically, like in a bit of a mathematical sense, if you've done much like advanced statistics, you might have come across these ideas of Markov processes. And like fundamentally, we say that the weather is a Markovian process. And it sounds like a fancy word. Really, what it boils down to is like it's supposed to be a memoryless process. So it's that I should be able to predict the evolution of the weather based only on what the current state of the weather is. That is what a Markov process effectively boils down to. In weather forecasting with these models, what we say is we relax it to a second order Markov process. What that means is not only will I give it the current state, I'll give it -6, so the previous state. And we've ran some like experimental ablations on giving it even more context, -12, -18. But we found that sort of like flattens out in effectiveness, probably because the model just doesn't have like enough capacity to pay attention to everything. So that's the answer if that was it. And then I guess if your question is like, why aren't you feeding it future information? That's because like in real time, I don't actually have the future information. So I shouldn't train it on anything that it won't actually get in real time. Cool, good question. Awesome. Any final ones? Otherwise, I'll leave you guys. It's a Friday evening. You probably want to go. Oh, thanks. Just for reference, Mirella is my mom. Hi, mama. Cool. I'll stick around for another
Perfect.
minute if there's
Thank
any final
you.
questions. Otherwise,
Yeah.
thanks, guys. Thanks for inviting me.
Meanwhile, if there's anyone that wants to ask any questions, feel free to write it at the end of the chat.
Yeah,
We'll take it as a final question. Otherwise, Andrew, thank you. There's not much to be said. This was
pleasure.
amazing. This was my favorite so far,
Amazing.
dare I
Do you
say.
say that to everyone?
Uh, no, no, no. I'm legit. Yeah,
Awesome.
this was really nice. It was really enjoyable, very straightforward, nice, and interactive along the way. So it's just sequentially beautiful to capture. So thank you once again for making the time for this to happen. I know
No, pleasure.
like there's Mina and L coming up, so I
Yeah,
didn't
I
know
have
if they'd
to
be
I have to
available, but
apologize because this is going to be very similar to the presentation I'll give at Mina ML, but
I'll think of different questions to ask.
okay, great. Awesome. Awesome. All right. Thanks, guys.
Perfect. Take care, everyone. Thank you
Cool.
once again,
Have a
and
nice weekend.
see you soon.
Bye.
Bye.